Hello for the first time class and welcome to Math 101. This first video is going to be just a bunch of review stuff. And that's really all we're doing kind of in this first week is just a bunch of review stuff, which makes this video a little bit on the longer side insofar as we do need to get through quite a bit of content. So I invite you to buckle up because we're going to get to a good amount of stuff here. And we're going to start off with expressions. All right, so an expression is made up of numbers and variables connected with mathematical operations. In essence, an expression is a mathematical entity, right? And it's just this thing that's made up of numbers and variables that's connected with mathematical operations. Operations being things like multiplication, addition, division, subtraction, squaring something, right? Square rooting something, throwing something into the tangent or arcsine function, right? There's a lot of different operations. A lot of different things you can write inside of a function that we would, in totality, call here's an expression, right? So like the tangent of theta plus pi over 2, that's still an expression, even though it's inside of a function, okay? But all that stuff comes at a much later time in your mathematical career. For now, we're really just going to be talking about these things here, the ones that I've explicitly listed. So a very brief example would be something like 3x plus 1. Right, it's got an addition sign in it. It's got 3 times x. It's got the number 1, right? So it's made up of numbers and variables connected with operations, right? 3x is connected with 1 via addition, right? 3x squared plus 1 is similarly an expression. This is also an expression. 3x squared plus b minus 17z to the 4th minus a million. Still made up of numbers, still made up of variables, still connected with mathematical operations, still just really addition. And subtraction, right? And that's it. As soon as you set it equal to 10, though, this whole thing ceases to be an expression. It's not an expression anymore. Now, what we'd say is that it's an equation. Now, you can say that it's an equation that's got a left-hand expression and a right-hand expression, right? Because that's really what an equation is. It's two expressions that are set equal to each other. But on the whole, right, this is not an expression. It's now an equation. But oftentimes what we try to do is manipulate one side of the equation, so manipulate one expression to isolate a variable. In this specific example, there's more than one variable, so this is kind of a complicated equation to solve if we don't know what some of the other variables are. But that's the difference between an equation and an expression. Equation has an equal sign in it, and it sets two expressions equal to one another. An expression is just a standalone thing with numbers and variables that are connected with mathematical operations. X, B, and Z, as I mentioned, those things are called variables. In this example, they're unknown. We don't know what they are, but sometimes you do know, right? Sometimes it'll say, here's an expression, right? Let's evaluate this for when X is equal to this thing, right? And then so we could figure out what either other variables are or what the value of the expression as a whole is. But variables are basically just placeholders for values that can change or vary, or there's specific unknown values that you're trying to solve for in certain equations. Evaluating an expression, just like I said, is when you plug in a known or given value for each variable, and then you calculate whatever the result is. So let's just work with one of the expressions that we were looking at before, which is 3x squared plus 1. And let's say that we want to evaluate, and that's the verb that you would use when you're going to do some kind of calculation by plugging in a specific value for a variable. Evaluate. Okay, so evaluate 3x squared plus 1 when x is equal to 2. And then let's also evaluate 3x squared plus 1 when x is equal to negative 5. So we'll start with 2 first. And usually what I do is I just put parentheses around any specific variable that we're plugging in for. And then I plug in the value that it says that it's equal to, right? So for me, I'd be like, okay, well, I'm going to put parentheses around this x, and that's where I'm going to plug whatever it is that we're plugging in. In this case, it's 2. Okay, so 3x squared plus 1 becomes 3 times 2, and then 2 is being squared plus 1. You got to be consistent with order of operations here, right? That whole PEMDAS thing, where we evaluate parentheses and exponents first. So I'm going to calculate this thing first, 2 squared, which is 4. Then I'm going to do 3 times 4, which is 12. Then I'll add 1. So 3x squared plus 1, when evaluated for x is equal to 2, has a value of 13. When we do -5, same deal, right? And the reason that the parentheses are important, right, putting the parentheses around the x, is because in this specific case, you're squaring -5, right? And when you square -5, it means to multiply -5 by -5. A negative times a negative is a positive, so we actually get 25 there. Multiplied by 3 is 75, plus 1 gives us a value of 76. You can also evaluate multivariable expressions, right? They would just have to give you all the values that you need to do the evaluation. So let's say that you have 2y times the quantity 1/2 x plus 9, and we want to evaluate this thing when y is equal to 3 and x is equal to positive 14. So, and really just to kind of emphasize my point, if one of these was not given, let's say they didn't give us this and it says evaluate this when y is equal to 3. We can't really do that, right? We're not going to get a number when we're done. We're going to get something that involves x, which is not really evaluation at that point. When you're evaluating something, you're usually going to end with a number, right, with a specific value. So I invite you to pause the video and give this one a shot. Plug in 3 for y and plug in 14 for x, and let's see what you get. Welcome back. Whether or not you pause the video, we're going to go ahead and go through this now. I'm just going to plug in 3 for y, again using the parentheses, and 14 for x. 2 times 3 is 6, right? That's where I'm getting this thing. 1/2 times 14, that's the same as 14 divided by 2, or 14 halves, which is 7. Before I do the multiplication of 6 with the 7, I'm going to have to do the parentheses first. So 9 plus 7 is 16. And then 6 times 16 gives us 96. And I showed the long multiplication there if you're interested on how I got that. All right, let's move on to the next topic. All right, so let's back up to when we were talking about an expression, specifically an expression that involves addition or subtraction. Because when an expression involves addition or subtraction, then we're talking about an expression that has more than one term in it. So I want to talk about what is a term. Okay, well, if we have the expression 3x plus 1, 3x is a term and 1 is also a term. If you have 2a squared b, 17a, and 11b, all connected with addition and subtraction, and that's kind of the key here, the fact that they're separated with addition or subtraction. Not in that order in this example, but you get the idea. 2a squared b, 17a, and 11b, those are all terms. So a term is like a single unit, right? That's all connected via multiplication or potentially division, right? Like this is a term. Let's do like 1/2 a to the 11th, right? Like that's a term. You could have something like 2a squared b divided by 3c, right? That's technically a term as well. It's not a monomial, though, and we'll talk about that at a later time when we start talking about polynomials, but it is a term. A term, definitively, is a number, a variable, or a multiplication of numbers and variables together with some exponents. It doesn't matter what the exponents are. The exponents could be negative, or they could be positive. They could be rational, right? And these are all things that we're going to talk about at some point. But for right now, we're going to keep exponents positive, and we'll talk about that stuff at a later time. So here are a bunch of terms. Every single one of these things is a term individually. There's no addition or subtraction anywhere with any of this stuff. Like terms are terms that have the same variables raised to the exact same powers. So I put some like terms on here. You can pause it if you want to try and find them, but I'm going to just go ahead and go through them. 7c squared d and 9c squared d are like terms because they have the same variables raised to the exact same powers. C is being squared, d is being raised to the first. Right? If one of these had a d to the third, then they're not like terms anymore. The number that's in front, oftentimes called the coefficient of the term, doesn't have to be the same. Right? So 7 and 9 aren't the same, but that doesn't mean that they're not like terms. It's just the variables and their respective exponents that make a term like or not. Here's another pair. 1/3 x squared y is a like term with 2/3 x squared y because they both have an x squared and they both have a y. And everything's being multiplied together within those terms. 123a and 24a squared are not like terms because on one of them, a is being squared. So again, kind of emphasizing the point, they have to be raised not only do they have to have the same variables, because these two terms that I've circled here do have the same variable, they both have an a, but they're not being raised to the same power. And that's what makes them not like terms in this case. Now, the whole point of knowing whether or not you're looking at like terms or not is because when you have a string of terms that are being added or subtracted, sometimes you can combine. Really, always you can combine like terms with addition or subtraction. So for example, 7c squared d plus 9c squared d, right? These are the like terms we were just looking at. You can add these terms together. And the way that I like to think about it is that c squared d is like an object, right? It's like you have a thing, right? So you have 7 of these c squared d's, and you've got 9 of these c squared d's. So how many of these c squared d's do you have? If you want, you can replace it with an object. It's like 7 oranges plus 9 oranges. Well, 7 plus 9, that's 16. So we have 16 oranges, but instead of oranges, they're actually c squared d's, right? And that's kind of how I think about how to combine like terms like this. So let's say that we want to simplify 1/3 xy plus 2/5 x squared y plus 2/3 xy minus 3/5 x squared y. Well, the first thing that I would do is I would look for, do we have any like terms here? There's 4 different terms, clearly. Not all of them are the same. Like right off the bat, I can tell you the first and second term of this thing are not like, but maybe there is another xy, right, that we can combine with the 1/3 xy. Maybe there's another x squared y that we can combine with the 2/5. Sure enough, there is. So we can simplify this thing, which is to say we can write it in a simpler way by just combining the like terms. So I'm going to reorganize this thing a little bit. First, we're going to notice that 1/3 xy and 2/3 xy are like terms. They're separated by addition. And so I'm going to add these two things together. When you have 1/3 plus 2/3, right, then you have 3/3. Right, 1/3 plus 2/3. You add straight across when you already have common denominators. So you get 3/3. That simplifies to just 1. 3 divided by 3 is 1. So those just simplify to being xy. 1. You could put 1 xy if you wanted to, but oftentimes when you're multiplying by 1, you can omit that number that's in front of them, which again is called a coefficient. I don't think I wrote that down anywhere though, but that is called a coefficient for that term. So those are taken care of. There is indeed 2 instances of x squared y. One of them has a coefficient of 2/5. The other one has a coefficient of negative 3/5. This one's a little bit more challenging because we're subtracting them, and you're actually subtracting a bigger number. So we know that we're going to get something that is negative. You can think about this in terms of the number line, right? We're starting at 2/5, right? And again, we've got 2/5 objects, right? We're subtracting away 3/5 of that same object. But you're subtracting away 3/5, so just move left on the number line 3/5. So the way that I drew the number line here is in terms of fifths. So 1/5, 2/5, 3/5, so on and so forth. And then in the negative direction, negative 1/5, negative 2/5. I'm just going to move 3/5 to the left because we are subtracting, and that lands us at negative 1/5 x squared y. Of course, you could just do the math too, right? 2/5 minus 3/5, the denominator's fifths. 2 minus 3 is negative 1. So negative 1/5 is going to be the coefficient, right? The number in front of x squared y. Done. All right. Now, when we're solving one-step equations, it is very like it sounds, I guess, maybe is the way to say that. There is only one step to solve for x. So solving an equation, in essence, is isolating a variable. Right? Getting a variable by itself and seeing what it's equal to. There's really 4 one-step equations that we're going to focus on for right now, but there are many different one-step equations because there's many different ways to write a one-step equation. But anyway, in this specific case, you want to try to undo the thing that's happening to x. So here we have 7x is equal to 42. X is being multiplied by 7, so we want to undo that multiplication of 7, and to do that, we're going to need to divide by 7. And the kind of rule for equations is whatever you do to one side, as long as you do it to the other side, your equation stays consistent, right? It stays balanced, if you will. So I'm going to divide both sides by 7. 7 divided by 7, that's 1, so those cancel. And then 42 divided by 7 is what we're going to be left with here, which is 6. Excuse me, I rewrote 42 as 7 times 6 just by factoring it into its two factors here, 7 and 6. So you have 7 in the numerator, 7 in the denominator, so those 7s are going to cancel. And so you get just 6, right, when you do this. 1 times 6, which is 6. That's it. That's the one step. The one step really is just dividing by 7 here. So if we just focus on these basic operations, addition, multiplication, subtraction, and division, then those are the only 4 types of one-step equations. If we let a and b be some constant juxtapose a variable means that it doesn't change. So a and b represent some kind of actual number. X is going to be the variable that we want to solve for in this case. So let's say that we have x plus a is equal to b, where a and b are constants. They represent some exact number. It could be whatever you want, right? Could be 7, like in our last example. This is just one step. To solve an x plus a equals b situation, you have to undo the addition that's happening to x. And the thing that undoes addition is subtraction. So you just subtract a to undo the addition of a, and your answer is just going to be whatever b minus a is. Maybe b is 11. So you have 11 minus 7, so 4, right, would be your answer in that example. The other one is subtraction, right? So this is x minus a is equal to b. To solve an x minus a equals b situation, you have to undo the subtraction, which is addition. So you add a to both sides, and your answer is whatever b plus a is. If we're using the 7 as a and b is 11 example, then we're at 18. The other one is a times x. So a is a coefficient. It's being multiplied by this variable x. To do that, it's just like the 7x is equal to 42 situation. You have to divide by whatever that coefficient is. So we're dividing both sides by a, and your answer is just whatever the fraction b over a is. In our first example, 42 divided by 6, or was it 7? 42 divided by 7, which gave us 6. Sometimes you do get a whole number. Other times you don't, right? It's okay to end up with, like, you know, I guess if we're continuing with the b is 11 and a is 7 example, this would be 11 sevenths, right? And that's the answer in this specific case. And then finally, there is a division equation. So you have your variable that's being divided by something, it's equal to b. The thing that undoes division is multiplication. So you're going to multiply both sides by a. And I guess the trick to this one, realize you're not multiplying by a over a. Like, that's a lot of things that I see students wanting to do, multiply by a over a. But that's just going to give you a squared in the denominator. So you're dividing by something bigger, potentially. So you're just multiplying by a in the numerator so that it can cancel with the a in the denominator. And then you do have to multiply the other side by a as well. So your answer just ends up being whatever a times b is. In our 7 and 11 example, we'd have 77. So here's an example. Let's say we want to solve 12x is equal to 3. Go ahead and pause it. See if you can do this one. All right, welcome back. You just divide by 12, right? So you get 3 divided by 12, which does simplify. 3 divided by 12. 12 is 3 times 4. So the 3's cancel, and you're just left with 1 over 4. And so that's your solution for this one. X is 1/4. All right, now modeling is more involved. Modeling, typically, we're talking about some kind of like a word problem, because modeling is a way to turn real life scenarios into some kind of mathematical structure. Typically, it's an equation, right, or a formula or something like that. So we write expressions and equations to quite literally model a situation. So for an example, I am just going to Google search Northwest natural gas prices in Monmouth. All right, so here's what we were able to gather from the Google search. We have a charge that's basically like a flat rate, and then we have a usage charge, which is based on the number of therms, right, that you use, and the rate for that is 0.86564, right? So 86 some odd cents, right? 86 point some cents. There's fractions of cents in this thing, but that's fine, right? Banks do that too, actually. I don't know why I'm telling you that. That's really not important. The point is, this is the rate, right, per therm that we're having to pay. A little less than $1 per therm. Okay, so what I want to do is I'm going to use a theoretical number here. Let's say that we use 24 therms of gas in a single month. So how much is my gas bill going to be if I use 24 therms? Well, we have to set up an equation, right? First, we're paying this flat rate of $8. And then we're going to add to that 0.86564 multiplied by the number of therms that we use. And I'm just going to use the variable t to kind of set up this equation. And that is going to be the total cost, right, of my specific bill. Okay? Well, I'm saying that we're using 24, right, in this example. So I'm going to evaluate, right, this thing at 24. I'm going to plug 24 right into that t. So first thing I have to do is multiply 24 by this decimal, right? And that's going to get me approximately 20.78, which I'll add $8 to, and that'll give me $28.78, right? And that's my bill, right? We're done. So that is probably a video on the longer side. I don't think I can say, I mean, hopefully not all the videos are going to be that long. There's just a lot to cover in this kind of introductory sort of video. But I appreciate you guys sticking it out. Usually what I try to do is I try to make videos that focus on one topic at a time. So there may be some, some class days where you're having to watch maybe 2 different videos, but that's because I like to keep things mostly just concise regarding a single topic. All right, so if you guys have any questions, make sure you leave a comment or send me an email. Thanks a ton for watching, and I'll see you in the next one.